This is the third problem in our 2021 dynamics review for the biomechanics course. In this problem, we're saying we have a spaceship coming into dock at a rotating space station. Telemetry tells us that the hub of the space station has a velocity as shown, and going in the negative x, negative y direction here. And we also know that the space station ports on the rim of the station are 100 meters from the central axis, and the station spins at a velocity of 0.6 radians per second. It wants us to find what the relative velocity of port B is with respect to our ship at the given time. So I'm going to call this center of the space station A, and I know that the distance from A to B, I'm just going to call my R, AB, is equal to 100 meters, right, just from our problem statement. And it's important for us to know, when looking at a rotating body, the velocity at any point, I'm just going to call it point B so we have it on the problem here, is equal to the velocity of some other point. In this case, we have point A, plus the relative velocity of the point we are of interest with respect to the point that we know. In this case, I'm going to the velocity of B with respect to A. And if we want to compare this to our previous notations, I'm going to note that B over A is equal to velocity of B with respect to A. That's just a convention I'm going to use for this problem to be clear about what we're calculating. We also know that the velocity of B with respect to A, if this is a rigid body, is going to be equal to omega, the angular velocity of the ship, crossed with the distance vector from whatever point we're looking at from A to B, right? So this omega of the body, and then R, which I've called before AB. Now I can leave these as vectors, but I have to define the third direction here, kind of the z-axis, if I want to do that. I can also do this as scalars, but just saying that we have omega, the magnitude, right, of the vector, times the magnitude of the R, AB, just as a distance. And then I have to figure out what the direction is based off of the trigonometry of what I have here on the board. So I'm going to do that just because it makes it easier for this 2D example. So in this case, we know our omega is 0.6 radians per second, and our R is 100 meters, right? And we should note that radians per second is unitless, so this is really just inverse seconds, right? So our velocity of B, really the magnitude, our velocity of B with respect to A, is equal to 60 meters per second, right? So that's my velocity of B with respect to A as just the magnitude. If I want to figure out the direction of this, since I know that this is my my negative x-axis here relative to my ship, right? I know that this vector here, right, is going to be aligned with my y-axis. So this vector here and this vector here are parallel to each other. And if that's the case, this is going to come off at 90 degrees from my r vector, right? So this vector for my velocity, my v of b with respect to a, is going to be also 60 degrees. So hopefully that makes sense there as how we get the 60 degrees out. And then we can get the components, right, the x and y components of this by just using the sine and cosine. In this case, the y is going to be the cosine, and the x is going to be the sine. So we'll say that our velocity of b with respect to a as a vector is equal to 60. And again, we said that the larger component here, the 60 degrees, is going to be our cosine, or sorry, our sine component, sine 60 degrees plus 60 cosine, cosine of 60 degrees. I'm running out of room on the edge of the screen there. So we can plug that into our calculator. and we get that our velocity of B with respect to A is equal to, in this case we have a positive, it will be positive in both directions. So 51, looks like 51.96, I'm just going to round that to 52. 52.0, comma 30, and that's going to be in meters per second. So that's the vector form, right? The vector of our velocity of B with respect to A. And I can look at that, and I think that makes sense relative to the coordinate system that I've defined for my spaceship there. So we have that. We go back to our first equation. We can say the velocity of B is equal to the velocity of A, which I sort of have this as Vs down here, but that's the same as the VA. So we have negative 30, negative 15, plus the B with respect to A, 52, comma 30. And so we get the total velocity as being 22, comma 15 meters per second. Which is interesting because we look at our spaceship here, even though our spaceship is approaching the station, it's actually getting further away from the port, right? And this would get further complicated by the fact that as the ports move, its velocity relative to the spaceship would change. And that's why docking is always difficult, right? All right. I hope that makes sense. And let me know if you have any questions.